Swayam Prabha. Digital India. Educated India.
So far we said that we are actually shining a plane polarized light and the molecule is either allowing it to go slow or allowing it to go fast. But that is not the only thing it can happen in a molecule, right? What else can happen? The molecule can absorb. That is the factor D we are talking about. The molecule can absorb. And a chiral molecule, again, as it sees the right hand and left hand circular polarized light differently, it can absorb one of them different to the other. What will be the effect of that? So let's take a look into it. So over here, I have a right hand circularly polarized light and I have a left hand circularly polarized light. And then I expose that to our sample. And again, I am drawing the RCP and LCP as different circles, but they are actually on top of each other. But again, for our better understanding, I am drawing it separately. Now, once it is going through that, my chiral sample can absorb either of them. And not only absorb, but it will also differentiate the absorbance. It will absorb one of them more than the other. Why? Because it is again a chiral molecule. And this can detect the chiral difference. And RCP and LCP are actually chirally different molecules. So it will detect the difference. What will be the effect? Now the effect is happening such that the RCP is remaining as it is, or it is absorbing pretty less. And it is moving like this with not much difference with respect to the amplitude it was having before it hits the sample. Whereas the LCP absorb more compared to the other. So that is why its amplitude goes lower. Now what will be the resultant values? So over here I am not showing anything that it is moving differently. It can, but we'll come into that later. Now we believe that this refractive index of RCP and LCP is remaining same. Just assumption for this moment. We are only considering the absorbance difference. Over there, what we are saying that the absorbance of the right hand circular polarized light and left hand circular polarized light are not same. Okay, and that is why we are seeing that you can see the left hand circular polarized light is severely diminished because it is getting absorbed, whereas right hand is not. So what will be the effect of that? So let's see. Previously, before it hits the system, what was the resultant? The resultant was that it was actually having a plane polarized light. Now what happens once these things comes? So let's put these things together. This is the right hand and this is the left hand on top of it, and I'm doing the resultant at the bottom. So it will be a large one because they're on top of each other. Then This is the right hand one, and this is the left hand one. Previously, because they are of the same amplitude, the resultant remain on the same position, but now it is going to be not in the same position. It's a vector algebra you can think about. So it will be somewhere rotated towards the right hand circular poised, right, because it has the higher amplitude. So altogether it is going to be in the same direction, but its amplitude is going to be lower compared to this first case, because over there both of them in the same direction, the blue right hand and the red left hand circular poised light. But now they're in the opposite direction. So that is why it is going to be moved towards the right hand circular poised light, because it has the higher amplitude. Then in this case, they're exactly opposite. If it is same absorbance, then it's going to be 0. But because they're different absorbance, their amplitude are not same for the right hand and left hand circular poised light. There are going to be some resultant, and it is going to be on the right hand circular poised light direction. And that is the minimum value you can have, because they're exactly opposite to each other and trying to cancel each other out. Then comes this one, which is exactly again very similar case to this, where we are going to get the value over here. And the last one, again they're on top of each other and they're going to show a value like that. So now these things are happening at the same place, although we are drawing in differently, but they're happening in the same place. Now if I combine all these 5 things together, what I'm going to get? So let's try to do that. First it was like this, then at the same point this, then this one, this, then this one, like this, then this one, like this. So altogether, if I draw it, what I'm getting? I'm getting nothing but an ellipse. So instead of a plane polarized light, what I'm going to get, if there is a different absorbance, what I'm going to get is an ellipse due to this different absorbance. So again, why it is happening? There is no change in the speed of the light, so they are moving in the similar speed, but their absorbances are different because one of them get absorbed more than the other. And what I'm saying, the resultant, it is happening such a way as you have drawn over there, it is going to show an ellipse instead of a plane polarized light. So again, I'm showing you the video of it, so take a look into it, and later on you can find out how it actually happens. So especially look at the bottom one over here. So you can see the left hand side figure is actually showing that before it hits the sample. So you can see the green and the blue color ones are actually have the same amplitude. So the resultant is actually the blue one is actually plane polarized light. But as soon as one of them is actually absorbed more than the other, now the red and green are not of the same amplitude. Even they're moving in the same speed, the resultant is actually not in a plane. The resultant is now moving in a elliptical motion. So that is why it is actually happening over there. It creates an ellipse out of it. Again, in your free time, take a look into that and try to figure it out if it is really making sense. If not, I will again go through that later. So far what we have learned that it might also happen that the right hand and the left hand circular poised light can actually absorb in different way, starting from this to so this is the right hand circular poised light. And this is the left hand circular polarized light, and we have our sample over here, my chiral sample. So previously what was actually a plain polarized light, after it has different absorbances, what I end up with is nothing but an ellipse. And over here, this ellipse I'm saying, it is actually a direct reflection of the fact that this chiral molecule can detect the difference between, again, the RCP and LCP. And over here, they're absorbing it differently. Previously, it was for the optical rotation, they're actually letting one of them move faster than the other because it is interacting one of them and slowing it down. Over here, it is much more direct. It is absorbing one more than the other. Over here, it is absorbing the LCP more than the RCP. And that is why the LCP light actually lowers down in amplitude, and that is why it ends up in an ellipse. Now an ellipse over here, this particular angle, say it is chi, we can say the tan of the chi value is nothing by minor axis divided by major axis. It is taken from the trigonometry lessons what we have learned in the 12th standard. So not going to details of that, but I'm just writing it. And minor axis over here is this one. And this minor axis is this one, and the major axis is this one. So we can write it in a way, the minor axis is nothing but AL minus AR, the difference between the absorbances of left hand and right hand circular polarized light. Whereas major axis is actually when they are actually in the same phase. So AL plus AR. Just going back over there, this is the major axis I'm saying because when they are on top of each other. So AL plus AR. And this is the minor axis. So this is AL minus AR. Okay. And this is AL plus AR. So over here, that I can write. And in generally, although I've drawn that ellipse in such a way, but in reality, the difference of AL and AR is so small that this actual angle of chi happens to be in the milli-degrees. So you can say the chi value, it's going to be very small. So in that way, we can say the tan chi value is going to be very similar to chi. And if you do some more math, I'm not going into the details, you can write this chi value as the following: 2.303 AL minus AR 180 by 4 pi, whereas these values are given in degrees. So AL minus AR is actually very small value, and it directly defines what will be my formation of the look of the ellipse, or this elliptical behavior, how much it will look like. This 2.303, you can imagine there is some log change from the natural log to the log base 10. And this again 180 by 4 pi, those values are radian to millidegree changes. So anyway, so those are not important things. What is the important thing is that this ellipticity, that how much is be the elliptical character, is actually directly dependent on the difference between the absorbances of left hand and right hand circularly polarized light. Very similar to the optical rotation, which is dependent on the difference of the refractive indices. And over here, the ellipticity value is dependent on the absorbances of the left hand and right hand circular polarized light. So go a little bit further. So you can say chi is dependent on AL minus AR, and which can be written as delta A. That means the difference between the absorbance of the left hand and right hand circular polarized light. Now we know absorbance is written as epsilon into CL, the Beer-Lambert's law. Now, if I want to write AL and AR values, which of these three parameters written over there, epsilon CL, will be showing the difference for the left hand and right hand circular porous light out of these three parameters? Anyone?
Epsilon.
Yes, thank you, Pooja. That's exactly correct. Epsilon value.
Epsilon.
Because, yes, that's true. Because concentration has nothing chiral in it. Path length has nothing chiral in it. Whereas we have discussed that epsilon value is something to do with the molecular property, which is known as the molar extinction coefficient, and has something to do with the oscillation. And this oscillation is a molecular property, so that will be the best bet for us that it is going to show some difference for the left hand and right hand circularly porous light. So I'm going to write it as ALCL, and this is epsilon RC. So I can write over here, this will be a difference of delta epsilon. C and L is a constant, so I'm moving it out. So it will be a function of delta epsilon. And as epsilon value is again a molecular property, so from there we can directly connect it to this ellipticity. So it is really showing that a molecular property is controlling how much of the ellipticity I'm going to find out. And this value can be also given as this molar ellipticity. And by the way, this phi value is defined as ellipticity. Similar to the optical rotation is given by phi. And this is written as 100 into psi is the value you have measured, C into L. So you are going to get a molar ellipticity. And this molar ellipticity value will be directly connected with delta epsilon. And this equation it values is 3300 into delta epsilon. So whatever the value you are measuring as from the ellipticity, you can convert it to a difference in the molar extinction coefficient. And that will be an independent property that you are measuring all over the galaxy, because it is a delta epsilon value. So it is not going to be dependent that much on the temperature or wavelength or anything. Okay. So that is what we actually measured. And over here, what we found, if I go back again, that from a linearly polarized light, from a chiral sample, what we actually ended up is actually an ellipse. And this value is known as the psi, and this is actually generally tends to be very close to 0. So this is known as the ellipticity. And this ellipticity is very similar to the optical rotation. It is a direct effect or result from a physical phenomenon. And what is the physical phenomena? That my right hand and left hand circularly polarized light is actually absorbed different amplitude. Okay, so this is RCP, this is RCP, this is LCP, and over here we found that this AL and A are not same, and that is why we are ending up to this ellipticity. So what is the phenomena that is resulting in this ellipticity? Very similar to the optical rotation, where we said it is a circular birefringence. Over here we call them circular because it is a different in circularly polarized light. Dichroism. Di means again different. Chroism, the term means color. That means two different color. Why two different color? Because it can absorb differently. because absorbance spectra is actually give you the colors. So circularly polarized light can absorb differently. So that reason is known as circular dichroism, and effect is ellipticity. So over here, if I want to combine those things together, so what you can get is the two factors over here. First thing is that right hand circularly polarized light and left hand circularly polarized light are there, but they are moving in different motions. So NL not equal to NR. And at the end, what is the effect you are going to see is the following. Is that it remains as a plane polarized light, but the original angle actually changes and you see an optical rotation. So over here, optical rotation is the effect, and cause, as we said, circular birefringence is the cause. Similarly, what might also happen that this right hand circularly polarized light and left hand circularly polarized light is moving in the same speed, but their absorbances are different. And as a result, what happens? What was previously a plane polarized light, now it becomes an ellipse. So we call them ellipticity. So ellipticity is again the effect, and the reason behind that is circular dichroism. And that is what it is actually happening in the real life. Now, we actually talk about them differently. Is it possible that the circular dichroism and circular birefringence can happen at the same time? Yes, it can happen, especially in the case of circular dichroism when an absorbance is happening. So circular birefringence can also happen. And at that time, how it will probably look like. So let's take a look back to that. So over there, that is how it actually looks like. So this is the light on the left hand side before it hits the sample. So it is a two circularly polarized light, same amplitude, same speed. You have a plane polarized light. Once it gets not only absorbed but also creates some difference in the refractive indices, you say the plane of the polarization changes. So you can see the ellipse is not in the same plane as the plane polarized light. It also has been rotated over here. And not only that, you can also see it actually creates an ellipse. So that is what happens in the real life. It shows both circular birefringence and circular dichroism. So that is what is actually going to happen if I have both the things coming together. So it is the RCP and say this is the LCP, and what is happening after it hits the chiral sample. So over here, it not only rotate faster, RCP, but it also get absorbed, the LCP. So that is why what it is actually going to happen, what you are going to see is actually the following: an ellipse which is going to be rotated on the right hand side. Why right hand side? Because I'm drawn in such a way that the RCP is moving faster than the LCP. So the plane will move on the right hand side from the beginning. So this angle will be the optical rotation. And not only that, because their absorbance is also different. So on this particular system, this is the minor axis, this is the major axis. So this angle will be the phi, the ellipticity. So from there you can actually measure both optical rotation and the ellipticity. So that what actually happens together. Optical rotation phi and ellipticity psi. Okay, so that is what is one of the main reasons why a chiral molecule actually rotates the plane polarized light. And today we learn about the circularly polarized light, and we also learn it is not only can rotate but also show an ellipse by creating difference in the absorbance. Now, two question remains. First one is much more simpler one, like which one of them we should use experimentally, the circular dichroism or circular birefringence, to monitor an enantiomer or enantiomeric excess or a chiral molecule. And the second, more important philosophical or fundamental question remains, like I understand that it can create the difference and it can detect the right hand and the left hand circularly polarized light, but why? What is there in a chiral molecule that it can separate this right hand and left hand circularly polarized light? So we have some clarification in our mind that the light itself is chiral, so that is why we can create the difference. But exactly what is happening in the molecule, how the molecular structure is connected such a way that it can interact with the light and see or detect the right hand and left hand circular polarized light differently. Those we'll be answering in the next class.